All right, guys. So now we are talking about your next part, which is your expectation, right? So when you talk about your expectation, please pay attention that we are talking about expectation under another measure, Q. So expectation depends not only on the random variable, but also on the probability measure used to weigh its possible value, right? Under the probability measure Q, right? We have this equation, which means that the expected value under Q of x equals the integral over capital omega of x of lowercase omega with respect to the probability measure Q of omega. Okay. Now, if you look at meaning of every term, capital X is the random variable. Capital omega is the sample space. Lowercase omega is one possible outcome. Capital Q is the probability measure used to weigh the outcome. The expectation operator with superscript Q makes the chosen measure explicit. The differential term means that integration is performed using your Q probabilities. The random variable may remain unchanged when the measure changes. What changes is the probability weight assigned to its possible outcomes. Why your Q matters in finance is in derivative pricing, Q of normally denotes a risk neutral measure. Under this measure, properly discounted tradable asset prices are martingales. Expected returns on tradable assets are adjusted to the risk-free rate after accounting for payouts such as dividends. Expected discounted payoff produce no arbitrage prices. The conceptual pricing formula is price at time 0 is equal to the expected value into Q of exponential raised to the power minus RT multiplied by the payoff. The lowercase r is the continuously compounded risk-free interest rate. Capital T is the time to maturity. The exponential term discount the future payoff back to time 0. The payoff is the derivatives cash flow at maturity, and expectation uses your risk neutral rather than real world probabilities. When the interest rate is constant and deterministic, right? The discount factor can be taken outside this expectation. Price at time 0 equals exponential raised to the power minus RT multiplied by the expected value under Q of the payoff, real world measure versus risk neutral measure. Real world measure used for forecasting reflects your estimated actual probabilities. Asset drift includes your risk premium used for portfolio risk, war, and expected returns. Risk neutral measure used for no arbitrage pricing reflects your market consistent pricing probabilities. Tradable asset drift becomes the risk-free rate after payout adjustment used for derivatives and hedging. Then we have your Gaussian theorem. Gaussian theorem provides the mathematical machinery for changing the Brownian motion drift when moving between the real world and risk neutral measure. The measure generally changes the drift but preserves the diffusion of volatility structure under the theorem's condition. Technical clarification here is that calling your Q probabilities, pair probabilities can be a little misleading, right? They are pricing probabilities consistent with no arbitrage, not necessarily forecast of what actually will happen. The markets are incomplete. There may be more than one risk neutral measure. Additional modeling or calibration choices are then needed. Okay. Then we have your, what do you say, Martingale, which we already discussed, and interpretation I told you is not correct, right? Technical clarification I gave. Then we go into your linearity of expectation. No independence needed. Basically, for your consistent or for your constants A and B and integrable random variables X and Y, your expected value of X plus or AX plus BY equals A multiplied by the expected value of X plus B multiplied by the expected value of Y, meaning lowercase a and b are fixed constants. Capital X and Y are random variables. The expectation of a weighted sum equals the same weighted sum of the individual expectation. The constants pass through the expectations operator. More importantly, X and Y do not need to be independent. They can be strongly, positively, or negatively dependent, and linearity still holds. Then we have your portfolio return application for a 2-asset portfolio. Expected return of portfolio is equal to the expected value of basically R sub P equals the expected value of W sub 1, R sub 1 plus W sub 2, R sub 2, which equals the W sub 1 multiplied by the expected value of R sub 1 plus W sub 2 multiplied by the expected value of R sub 2. Capital R sub P is the portfolio return, capital R sub 1 and R sub 2 are the two asset returns. Lowercase W sub 1 and W sub 2 are the portfolio weights. Expected portfolio return is the weighted average of expected asset returns for a fully invested two asset portfolio. The weights usually satisfy W1 plus W2 is 0. The weight condition is a portfolio constraint, not a requirement for linearity itself. Then you look at the diagram. The diagram places the two individual expectation of a horizontal value line, expected value of X and expected value of Y for a weight between 0 and 1, right? So W is greater than or equal to 0 or less than or equal to 1. The expectation on the weighted combination is given by this equation. The expected value of Wx plus 1 minus W multiplied by Y equals W multiplied by the expected value of X plus 1 minus W multiplied by the expected value of Y. Because the weights are non-negative and add to 1, the resulting expectation lies between the two individual expectations shown in the diagram. Finance uses are calculating your expected portfolio returns, decomposing your expected derivative payoff, aggregating expected losses and loss exposure, pricing portfolio instruments under the risk neutral measure. Technical clarification again is expected return is linear, but portfolio risk is generally not. Volatility and variance depend on covariance and therefore calculate diversification and dependence between assets. Okay. With that, we move to your next slide, which is slide number 20, expectation concept. Monotonicity of expectation. Basically, suppose one random variable is no greater than another almost surely. So X is less than or equal to Y almost surely means that the inequality holds with probability 1. Okay. So that is probability of X is less than or equal to Y equals 1. If both expectation exists, monotonicity implies this. Basically, expected value of X is less than or equal to the expected value of Y. Intuitively, please understand that if X never produces a higher value than Y, apart from possibility on a probability 0 set, its probability weighted average cannot exceed the average of Y. Financial example is, suppose two derivative payoffs satisfy this condition, which is P sub 1 of omega is less than or equal to P sub 2 of omega. Capital P sub 1 is the first payoff, capital P sub 2 is the second payoff. Lowercase omega identifies the market scenario. The second product pays at least as much as the first in almost every scenario. The expected payoff must satisfy this equation, which is the expected value of P sub 1 is less than or equal to the expected value of P sub 2. With the same maturity and discounting convention, the second product should not be worth less than the first, otherwise the payoff ordering could create an arbitrage opportunity. Almost sure versus impossible. Please understand, almost surely does not mean that the violation is logically impossible. It means that the set of violating outcomes has probability 0. The probability 0 event can still contain possible outcome. Therefore, an impossible event is an empty set. An almost surely statement may fall or may fail on a non-empty null set. So the probability 0 treats that null set to irrelevant for expectation and integration. Okay. Then we get into the next part. Slide number 21, we are looking at Jensen's inequality, convexity plus financial meaning. If phi is a convex function, right? Phi of the expected value of X is less than or equal to the expected value of phi of X. Meaning there are two different procedures here, right? So first average X, right? And apply the convex function. First apply the convex function to every possible value of X and then average the result. For a convex function, the second procedure produces a value at T such large as the first. We have definition of convexity, right? A function is convex when your P of your lambda x1 plus 1 minus lambda x2 is less than or equal to lambda phi of x1 plus 1 minus lambda phi of x2, right? So you have 0, lambda 1. So phi of lambda x sub 1 plus 1 minus lambda multiplied by x sub 2 is less than or equal to lambda phi of x sub 1 plus 1 minus lambda multiplied by phi of x sub 2, where lambda is between 0 and 1. So please note that lowercase x sub 1 and x sub 2 are two possible inputs. Lambda is the weight between 0 and 1. The left side evaluates the function at the weighted average profit. The right side takes the weighted average of the function values. If you look at diagram, the horizontal axis contains possible input values including x1 and x2, x sub 1 and x sub 2. The vertical axis phi x, phi of x, the solid curve is the convex function. The dashed straight line joins 2 points on the curve and it's called the chord. The diagram also presents Jensen inequality in the reverse order, right, which is given by this equation. Basically, the expected value of phi of x is greater than or equal to phi of the expected value of x. This is mathematically identical to the box inequality. Technical clarification here is that slide's wording says that the convex curve lies above the chord. That wording is actually reverse. For a convex function, the chord lies above or on the curve, right? The diagram itself correctly shows the dash chord above the solid curve, right? So just small typo, right? Basically, the chord lies above or on the curve, right? Chord lies above or on the curve. Okay, the diagram itself correctly shows the dashed chord above the solid curve, right? Financial meaning here is that a call option payoff is convex in the underlying asset price, holding the mean terminal price constant. Greater dispersion can raise the expected option payoff because downside payoff is limited at 0, upside payoff continues to increase. Larger favorable movements contribute more than equally large unfavorable movements subtract. Jensen's inequality, therefore, helps explain why volatility has positive value for option holders. If you look at concave utility, the expected value of U, right, is less than or equal to U of the expected value of W, right? So if you look at the risk averse investor with the concave utility function, okay, please note the expected value of U of W is less than or equal to U of the expected value of W, right? Capital W represents wealth, lowercase u is a utility function. The inequality reverses because the utility function is concave, right? And uncertain wealth provides less expected utility than certain wealth equal to its mean. Okay. So basically, uncertain wealth provides less expected utility than certain wealth equal to its mean. Okay. And then we get into the next part, your 22, right? So here we have another equation. We are still doing your expectation concepts, right? And in expectation concept, we will look at. So Fatu's lemma, MCT, DCT, limits of expectation, right? So basically, these results determine when your limits can safely interact with expectations. The important bit when random variables arise at limits of approximations. Fatu's lemma for a sequence of non-negative random variables, your expected value of the limit inferior as n approaches infinity of x sub n is less than or equal to the limit inferior as n approaches infinity of the expected value of x sub n, right? Basically, meaning is capital X sub n is the nth random variable in a sequence. The limit inferior captures the eventual lower limiting behavior of the sequence. Fatu's lemma says that the expected value of the limiting lower behavior cannot exceed the limiting lower behavior of the expectation. technical clarification here is the slide does not state the standard non-negativity assumption. Part 2 lemma in this form requires the sequence to be non-negative. More general versions are possible when an integrable lower bound exists. Then we have another equation called monotone convergence theorem. So the assumptions are that 0 is less than or equal to x sub n and x sub n increases to x. This means every random variable in the sequence is non-negative. The sequence increases pointwise or almost surely towards x. Each successive approximation is at least as large as the preceding one. The conclusion is this. The expected value of x sub n increases to the expected value of x. The expected value converges upward to the expectation of the limiting random variable. The theorem permits the limiting operations to pass through the expectation for increasing non-negative approximations. Then we have your dominated convergence theorem. The first condition is almost pure convergence. X sub n converges to x almost surely. The second condition requires a dominating random variable, which is this. The absolute value of x sub n is less than or equal to y. Capital Y provides a common upper bound for the absolute value of all approximation. The domination must hold almost surely. The dominating variable must be integrable, right? The expected value of the absolute value of y is less than infinity. Under these conditions, we get this. The expected value of x sub n converges to the expected value of x. Equivalently, the limit and expectation may be interchanged, right? We can write as limit n tends to infinity, expected value of xn is equal to expected value of infinity. The limit as n approaches infinity of the expected value of x sub n equals the expected value of the limit as n approaches infinity of x sub n, right? Financial application is establishing convergence of discretized stochastic processes passing from discrete approximation to e to the integral, showing that approximated derivative payoffs converge to the exact expected payoff, justifying your limiting arguments in stochastic differential equations numerical schemes, supporting a convergence argument for Monte Carlo estimators. You need technical clarification. The law of large number is the main theorem behind ordinary Monte Carlo average convergence. Dominated convergence is often used in related steps, such as proving that approximate payoff or your discretized path converge in expectation, right? So that is what we have understood. Then we get into next slide, slide number 23. So next one is transformation of random variables y equals g of x, right? So capital X is the original random variable, lowercase g is a deterministic function. Capital Y is the transform random variable. Once x is realized, applying the function determines y. The notation for a general function is g of dot, right? The dot is a placeholder indicating that the function can be evaluated at an input. The main objective is, given the distinction of x and the function g, we may want to find the distribution of y, calculates its CDF, calculates its BDF where density exists, calculates its expected value, understand how the transformation changes, Q-ness, support, and tail be given. If you look at the financial example, right, derivative payoffs can be written as a function of the terminal asset price, such as your H is equal to G ST. H equals G of S sub T. Capital H is the terminal payoff. Capital S sub T is the terminal asset price. The payoff function converts the terminal price into cash flow. Example includes your calls, your puts, your digitals, and barrier dependent payoff. Other applications include transforming normal log price into positive stock prices, transforming returns into prices, applying floors or caps to interest, applying non-linear volatility transformation, converting risk factor into portfolio losses. Non-linear transformation can significantly change a distribution. Asymmetric input distribution can produce a skewed output distribution. Okay. Then we get into your slide number 24, which is distribution of y equals g of x. right? The CDA method begins the definition of the transform variable distribution, which is given by this equation: f sub y of y equals the probability that y is less than or equal to y, which equals the probability that g of x is less than or equal to g. Lowercase y is the possible value of the transform variable. The CDF gives the probability that the transform value does not exceed y. Replacing y with this definition convert the event into a condition involving x, strictly increasing your transformation, right? If g is strictly increasing, g of x is less than or equal to y if and only if x is less than or equal to g inverse of y. The double arrow means if and only if the inverse function recovers the original input corresponding to y. The superscript -1 denotes an inverse function, not a reciprocal. The transform CDF becomes this, basically f sub y of y equals the probability that x is less than or equal to g inverse of y, which equals f sub x evaluated at g inverse of y. Because an increasing transformation preserves ordering, the inequality direction remains unchanged. Strictly decreasing transformation, when you talk about it, g is strictly decreasing. Your g of x is less than or equal to y if and only if x is greater than or equal to g inverse of y. Because the decreasing function reverses ordering, then equality kind of changes direction, right? For a continuous random variable, the slide formula is this: f sub y of y equals the probability that x is greater than or equal to g inverse of y, which equals f1 minus f sub x evaluated at g inverse of y, right? So the last equality assumes that x has no point mass at the inverse threshold. It is therefore correct for a continuous x. For a general distribution containing atoms, the precise expression uses the left-hand limit of the CDF, which is your one minus your f of x So f sub y of y equals 1 minus f sub x evaluated the left-hand limit of g inverse of y. The left-hand limit excludes the probability mass located exactly at the threshold from the amount being subtracted. The formula also applies only when y lies inside the range of the transformation. Outside that range, the CDF must be set to 0 or 1 as appropriate, right? Then we go into the next part, which is your line number 25. Assume the transformation is monotonic, right, and differentiable. The original random variable has a density. The transformation can be inverted over the relevant range. The relationship between the original and transform variable y is equal to gx and x is equal to g inverse of y. The density of the transform variable is given by this equation: f sub y of y equals f sub x evaluated g inverse of y multiplied with the absolute value of the derivative with respect to y of g inverse of y. So the inverse function identifies which original value produces y. The original density is valued at that original value. The derivative measures how the transformation stretches or compresses the numerical scale. The absolute value guarantees that the transform density remains non-negative, right? So why the derivative is kind of necessary. Basically, suppose a small interval in the original variable is transformed into a much wider interval. The same probability is now spread over more space, so the new density must be smaller. If the transformation kind of compresses an interval, the density becomes larger because the same property is concentrated into less space. The scale adjustment is called the Jacobian adjustment. Okay, so keep that in mind. An equivalent form is your given by this equation, basically f sub y of y equals f sub x of x divided by the absolute value of g prime of x evaluated at x equal to g inverse of y. The prime denotes the derivative of g with respect to its input. A large transformation slope spreads probability out and reduces density. A small transformation slope compresses probability and increases density. Why the absolute value appears? A decreasing transformation has a negative derivative. Without the absolute value, there are formula could produce a negative density, which is impossible. The absolute value preserves the magnitude of the scale change while removing its direction. Then we have your kind of normalization check. The transform density must satisfy the integral from minus infinity to positive infinity of f sub y of y dy equals 1, right? This confirms the total probability remains 1 after the transformation, right? Again, technical clarification here is the formula shown applies directly when the transformation is 1-to-1 and monotonic. If several original values produce the same transform value, the density contributions from all valid inverse branches must be added. Okay. Now we go to the next slide, slide number 26. So now here in slide number 26, we are talking about transformation of random variables. Basically, we are trying to establish quant connection, quant finance example. Your S equal to exponential raised to x creates a log normal distribution, right? So we start with a normally distributed random variable, which is given by this equation. X is distributed as a normal random variable with mean mu and variance sigma squared. Capital X can represent a log price. Mu is the mean of the log price. Sigma squared is the variance of the log price. Sigma is its standard deviation, right? So that we have, and now apply the exponential transformation. Your S equals g of x, which equals exponential raised to the power of x. Capital S is the transform variable interpreted as the price, lowercase g is the transformation function. The exponential converts the unrestricted normal variable into a positive variable. Because an exponential is always positive, right? So S is greater than 0. This property makes the transformation suitable for stock price modeling because it prevents your negative prices. And then we have inverse transformation, taking the natural logarithm and reverse the exponential transformation, right? Which is this. The complete conclusion is this. Basically, S equals exponential raised to the power x, which implies that S is log normally distributed with log location parameter mu and log variance parameter sigma squared. The financial meaning here is that if the log price is normal, the price itself is log normal. The transformation is useful because it keeps stock price positive, represents multiplicative rather than additive price growth. Produces analytically manageable price distribution, supports a closed form pricing in the Black-Scholes model, provides a sample method for Monte-Carlo path generation. And then we need a technical kind of clarification. The parameters mu and sigma squared are the mean and variance of the logarithm of S. They're not the mean and variance of S itself. A log normal distribution is right skewed. Its downside is bounded by 0, while its upside is theoretically unbounded. Okay, so that is what. And then we get into your slide number 27. X is distributed as a normal random variable with mean mu and variance sigma squared. And S equals exponential raised to the power x for a positive value of S. Log normal density is given by this equation. F sub S of S equals 1 divided by S sigma times the square root of 2 pi multiplied by the exponential or minus the square of natural log S minus mu divided by 2 sigma squared for S greater than 0. And if you look at meaning of every term here, the lowercase s is a possible realized value of S. The function on the left is the log normal probability density. Mu is the mean of the underlying normal variable. Sigma is the standard deviation of the underlying normal variable. The natural logarithm converts it back to the normal scale. The factor involving 1 divided by S is the Jacobian adjustment, right? For non-positive value, the density is given by your F, right? For F sub S of S equals 0 for S less than or equal to 0. If you derive the density for the inverse transformation, here is this. G inverse of S equals the natural logarithm of S. The derivative of the inverse transformation is given by this. The derivative with respect to S of the natural logarithm of S equals 1 divided by S. You apply the Jacobian formula, it gives you this equation. F sub S of S equals F sub X valued at the natural logarithm of S multiplied by 1 divided by S. The original normal density is valued at the corresponding log value. The factor involving 1 divided by S adjusts for the exponential transformation change of scale. The key property here is this, where the natural logarithm of your S is normally distributed with mean mu and variance sigma squared, which implies that S is log normally distributed. This equivalence allows a difficult looking positive price distribution to be analyzed through a simpler normal log price. Okay. Then we get into the next part, which is transformation of random variable, where this appears in quant finance. Basically, you look at Black-Scholes and GBM under your geometric Brownian motion. GBM, your Geometric Brownian motion implies that S sub t is log normally distributed. Your log returns are normal under the GBM assumption. Transforming the normal log price back to the exponential function produces a log normal stock price. This distributional structure makes the Black-Scholes closed form formula possible. Then we have Monte Carlo simulation, basically generates a normal or standard normal random variable, right? That is distributed as a standard normal random variable with mean 0 and variance 1. The next GBM price is simulated using this equation, basically S sub t plus delta t equals S sub t multiplied with the exponential of open square bracket mu minus 1/2 sigma squared multiplied by delta t plus sigma times the square root of delta t times z close square bracket. Capital S sub t is the current price. Capital S sub t plus delta t is the next simulated price. Mu is the real world drift when forecasting your price path. Sigma is volatility. Delta t is the simulation time step. Capital Z is the randomly generated standard normal shock. The term involving 1/2 of variance is the Ito's correction. The square root of term gives the shock the correct variance, right, for constant drift and volatility, right? This is an exact one-step GBM transition rather than a simple Euro approximation, right? Then we have risk neutral simulation also. For derivative price in the real world drift is replaced by the risk-free adjusted for continuous dividends, right? So S sub t plus delta t equals S sub t multiplied by the exponential of open square bracket R minus Q minus 1/2 sigma squared multiplied by delta t plus sigma times the square root of delta t times the close square bracket, right? So we have that. Okay. So that is very, very important to understand. Okay. So again, I think most of the things are already clear, right? So you understand here lowercase r is the risk-free rate, lowercase q is the continuous dividend yield. This version generates your risk neutral path for the derivative valuation. It should not be interpreted as a forecast for stock actual expected return, right? So that is what we need to keep in mind, right? So basically, what you have to understand is, I think I have written again and again, but the idea is very simple that this can be written as what I told you, yes, right? I'm just writing it, even though you have already written it earlier also. Okay. So then we go to stochastic volatility and log price modeling. Basically, many models work with the natural logarithm of S sub t. Log price are often easier to analyze because they convert multiplicative price changes into additive changes. The model then transform back to the price, which is this one. S sub t equals exponential raised to the power natural logarithm of S sub t. The transformation therefore allows complex positive price behavior to be studied through more manageable variables. Okay. Main takeaway is transformation converts complex price behavior into simpler normal based calculation. Okay. Then we go into the next part. We'll look at moments, your variance and covariance, right? And we look at moments measuring your distribution shape. So the kth raw moment of random variable is given. The expected value of x raised to the power k. Capital X is the random variable, lowercase k identifies the order of the moment. Raw means the power is taken around 0 rather than around the mean. First raw moment we have, which is k equal to 1. That first raw moment is nothing but your expected value of your x, right? This is the mean or probability weighted average. In finance, it may represent an expected return, expected loss, or expected payoff. Second raw moment is k equal to 2. The second raw moment is expected value of x squared. It measures the average value or average squared magnitude and is used in calculating your variance. Raw moment versus central moment. The kth central moment is given by your this equation. Basically, the expected value of open parenthesis x minus the expected value of x close parenthesis raised to the power k. Central moments measure deviation around the mean rather than around zero. Then we have skewness. Skewness of x equals the expected value of open parenthesis x minus the expected value of x divided by sigma sub x close parenthesis cube. Skewness measure asymmetry. Positive skew means a longer or more influential right tail. Negative skew means a longer or more influential left tail. Equity index return often display negative skew because large downside moves can occur here suddenly. Then we have your kurtosis. Kurtosis, if I have to put equation, basically kurt of x is equal to given by this expected value of this equation. Kurtosis of x equals the expected value of open parenthesis x minus the expected value of x divided by sigma sub x. Close parenthesis raised to the fourth power. Kurtosis measures the importance of extreme standardized deviation. High kurtosis is associated with a greater tendency toward extreme observation than under a normal benchmark. If you look at financial interpretation, you have moment related quantity, right? So if you're looking at mean, financial meaning expected or unexpected loss. If you're looking at variance, dispersion of return. If you're looking at skewness, which is asymmetry between upside and downside. If you're looking at kurtosis, which is exposure to unusually extreme movements, right? So again, technical clarification which you need here is that variance is the second central moment, not simply the second raw moment. Similarly, skewness and kurtosis are standardized central moments. Raw higher moments alone do not directly equal skewness or kurtosis. Okay. Then we go into the next part, which is your slide number 30. We again keep our focus on moments, variance, and covariance. We look at measuring your risk volatility, right? So variance measure the average around deviation from the mean. Variance of x equals the expected value of open parenthesis x minus the expected value of x close parenthesis square, meaning subtract the mean from each possible value, square the deviation so that positive and negative deviation do not cancel. Take the probability weighted average of the squared deviations. A variable concentrated near its mean has low variance. A variable with widely dispersed values has high variance. You have your computational form here. Variance of x equals the expected value of x squared minus the square of the expected value of x. This form is often more convenient because it requires the first and secondary raw moments. You have the standard deviation here. Sigma sub x equals the square root of the variance of x. Standard deviation expressed in the same unit as the original random variable. Variance is expressed in squared units. For return, standard deviation is normally called volatility. Technical clarification here, which is very, very important, is that variance and volatility are related but not identical. Variance is the square of volatility. Volatility is the standard deviation. Saying variance is volatility, therefore an informal shorthand, right? Financial application is mean, variance, portfolio optimization, risk budgeting, volatility targeting, value at risk model, option pricing, position sizing. Variance treats your favorable and unfavorable deviation symmetrically. It does not separately capture your downside risk, skewness, or tail severity. Therefore, it is commonly supplemented by measures such as expected fall, shortfall, and downside deviation, right? We need to keep in mind that part. Then we go into your 31, which is again, we are still focusing on covariance, measuring the dependence between your two random variables. Okay, so covariance measure whether two random variables tend to be above or below their respective means at the same time, and definition is this: covariance of x and y equals the expected value of open parenthesis x minus the expected value of x close parenthesis multiplied by open parenthesis y minus the expected value of y close parenthesis, when both variables are simultaneously above or below their mean. The product of your deviation is positive and one is above its mean, on the other is below, the product is negative. Expectation averages these products across your outcomes. So computational form is your this also covariance of x and y equals expected value of xy minus expected value of x multiplied by expected value of y. Okay, so positive covariance, we have covariance of x and y is greater than 0. The variable tend to move in the same direction related to their means. Negative covariance is this. Covariance of x and y is less than 0. Basically, the variable tends to move in opposite direction related to the mean. Then we have zero covariance, covariance of x and y equals 0. This means there is no linear dependence captured by covariance. It does not necessarily mean the variables are independent. They may still have a non-linear relationship, right? And then we look at the correlation, which standardized covariance, basically rho sub xy equals covariance of x and y divided by sigma sub x times sigma sub y, where rho sub xy lies between -1 and +1. Rho is the correlation coefficient. Your the denominator divided by both standard deviation. Correlation is unit free. Positive one represents perfect positive linear relationship or association. Negative one represents perfect negative linear association. 0 represents no linear association, no linear correlation. Okay, and which is very, very important to understand. So correlation is undefined if either variable has 0 standard deviation, right? So keep that in mind. When you look at portfolio variance connection here, for a 2-asset portfolio, we have your variance of plus of x. Okay, so basically variance of w sub x times x plus w sub y times y equals w sub x squared multiplied by variance of x plus w sub y squared multiplied by variance of y plus 2w sub x w sub y multiplied by covariance of x and y, right? This equation shows where diversification comes from if covariance is low or negative. Portfolio variance can be lower than a simple weighted average of individual risk. Okay. Then we go to your slide number 32. Basically correlated Brownian motions in finance models. Two correlated Brownian motions are commonly represented by this equation: dw sub t superscript 1 multiplied by dw sub t superscript 2 equals rho times dt. The two differential terms represents Brownian shocks from two sources. Rho is their instantaneous correlation. The term dt is the infinitesimal time increment. The correlation parameters satisfy your this equation. Basically, rho belongs to the closed interval from -1 to +1. Positive correlation greater than or equal to 0. Rho, how to understand is that rho is greater than 0. The two Brownian shocks tend to have the same sign. Negative correlation, rho is less than 0. The shocks tend to have opposite signs. Zero correlation, rho equals 0. So in the standard jointly Gaussian Brownian construction, zero correlation implies independent Brownian shocks. Technical interpretation here is the product of Brownian differential is Ito's shorthand for the instantaneous quadratic covariation. The more rigorous representation is given by this equation. The differential of the quadratic covariation of W superscript 1 and W superscript 2 at times t equals the rho times dt. It should not be interpreted as ordinary multiplication of two conventional infinitesimal numbers. Then we have Monte Carlo construction also. A correlated second Brownian shock can be generated from your independent Brownian shocks, which is given by your equation such as dw sub t superscript 2 equals rho times dw sub t superscript 1 plus the square root of 1 minus rho squared multiplied by dz sub t. Okay, the z shock is an independent Brownian shock. The first term creates correlation with the first Brownian motion, and the second preserves the total variance. You have your financial applications here, multi-asset and basket option pricing, your correlated foreign exchange and interest rate models, credit portfolio simulation, index option pricing, stochastic volatility models. In the Heston model, the asset return shock and variance shock are often negatively correlated. This captures the equity leverage effect. And falling equity prices are frequently associated with your rising volatility. Okay. Then we go into your slide number 33, basically conditional expectation, definition, and meaning. And suppose the available information set is a sub sigma algebra of full information at this equation. Basically, script G is a subset of script F. Script F contains all measurable information in the overall model. Script G contains only the information currently available, right? And a smaller sigma algebra represents less information. The conditional expectation is given by this formula. The expected value of x conditional of script G. Conditional expectation is still a random variable. Its value depends on which information contains script G has been observed. It must be measurable with respect to the available information, which is given by B. And the expected value of x conditional of script G is script G measurable. This means the conditional expectation can depend only on information contained in script G. It cannot use information that has not yet been revealed. We have your formal defining property also here, right? The formal defining property is for every measurable event A contained in script G, we will say basically the integral over A of the expected value of x conditional of script G with respect to P equals the integral over A of x with respect to P for every A belonging to script G. The conditional expectation matches the probability weighted value of x over every event that can be identified using the available information. Unconditional versus conditional expectation, we need to understand that unconditional expectation uses the full distribution without new observation, usually produces one fixed number, represent the prior average. Conditional expectation incorporates currently available information, produces a random variable depending on the observed information, and represents the updated average. Then we have time-based information. At time t, available market information is represented by your ft, basically script f sub t. The expectation of future quantity using time information is given as this value is expected value of x conditional script f sub t. Information may include current and historical asset prices, interest rate, volatility, observation, and other market variable observed by time t. Then, if you look at the technical clarification here, conditional expectation is often called the best prediction, more precisely when the relevant variables have finite second moment. It is the best mean squared error prediction based only on the available information. Okay. Then we get into the next part, which is why your conditional expectation is central in quant finance. Basically, under the risk neutral measure, the value of maturity payoffs and earlier time is given by this equation. Basically, V sub t equals the expected value under Q of exponential raised to bar minus R multiplied by capital T minus T multiplied by the payoff at capital T conditional on script F sub T. If you look at meaning of every term, capital B sub T is the derivative value of time T, capital Q is the risk neutral probability measure. Lowercase r is the constant quantimistic compounded risk-free rate, capital T is the maturity rate, capital T minus T is the remaining time to maturity. The payoff sub T is the cash flow received on maturity. Script F sub T, right, is all market information available at time T. The formula perform two operations. You discount the future payoff from maturity back to time T and average that expected or average the discount payoff using risk neutral probability conditional current information, right? Why the value changes to time? Because as time passes, information set expands, new asset prices, volatility level, and interest rate become observable. conditional expectation incorporate the new information and update the derivative sphere value. Right? Then we have a general stochastic form, right, which is nothing but so again v sub t equals the expected value under q of the exponential of minus the integral form t of capital T of r sub s ds multiplied by the payoff that capital T conditional script f sub t, right? Lowercase r sub s is the short rate at time s. The integral accumulates interest rate between valuation, time, and maturity. The exponential converts the accumulated rate into a stochastic discount factor. There's a connection to a Martingale theory also using the money market account as numeraire. We have V sub t divided by B sub t equals the expected value under Q of the payoff at capital T divided by B sub capital T conditional script F sub t. Capital B sub t is the value of the money market account at time t. The left side of the discounted derivative price. The right side is the conditional expectation of the discounted terminal payoff. Therefore, the discounted price process is a Martingale under the risk neutral measure. Why conditional expectation is kind of crucial? Because it expresses fair value using currently available information. It provides the foundation for Martingale pricing. It connects terminal payoff to present values. It is central to solve your PD-based pricing models. It supports your dynamic hedging because prices are updated continuously as information changes. That it separates your forecasting in the risk real world measure from pricing in the risk neutral measure. Okay. Then we go to next slide, slide number 35. We have practice questions now. We have to do it. Okay. Okay, so now we are doing your slide number 35, right? In slide number 35, we are looking at your questions, right? So question number one is, problem number one is about your continuous random variable expectation, right? So if you look at it, right, the question says that let x be a continuous random variable with density given f sub x of x equals 2x, where x is greater than or equal to 0 and less than or equal to 1. So the question is asking you the expected value. Okay. So first of all, you check that this is a valid density or not, right? How do you do it? You take the integral from 0 to 1 of your 2x dx equal to 1. The density is non-negative over its support and its total area is 1. Okay. So correct answer for this thing here, for a continuous random variable, the expected value is equal to 0 to 1 x fx dx okay 2 by 3. So the expected value of x equals the integral from 0 to 1 of x multiplied by f sub x of x dx, which equals the integral from 0 to 1 of x multiplied by your 2x dx, which equals your 2/3, right? So correct answer is 2 by 3. So why it is correct? Because see, expectation weight or weighs each possible value by its densities. In the density increases with x, higher value receives greater weight. So the mean lies above the midpoint of the interval. And please understand it is not a multiple choice question that you have to calculate it, right? So we have done it, right? Then we go to next question, problem number 2. Discrete random variable expectation. Let x take values 1, 3, 5 with probabilities probability of x is 1 equal to 1 equal to 0.2, probability of x is equal to 3 is equal to 0.5, probability of x is equal to 5 is equal to 0.3. The probability that x equals 1 is 0.2, right? Next equal to 3, 0.5, probability x equal to 5 is equal to 0.3. So correct answer in this case is expected value of x 1 into 0.2, 3 into 0.5, right? And your 5 into 0.3, 3.2. Okay. Then we get into next part. Compute your expected value of exponential x for x, which is distributed as standard normal random variable with mean 0 and variance 0, right? So we have to calculate the value, right? So please understand, when we are calculating expected value of your exponential x is equal to e mu plus your half sigma square, right? The expected value of exponential raised to the power x equals exponential raised to the power mu plus 1/2 sigma square, right? Here the mean is mu is 0, sigma square is 1, right? So expected value of y, the expected value of, okay, the expected of y, the expected value of y equals the expected value of exponential raised to power x, which equals exponential raised to the power 1/2, right? So your expected value of your y is equal to exponential 1/2 by 2. So till now, easy questions, right? Question number 4, right? Applying your monotone convergence theorem. So the original random variable is non-negative, right? X is greater than or equal to 0. The truncated sequence is given here. So x sub n equals a minimum of x and n. This means that value of x above n are capped at n, while values n below n remain unchanged, right? So the required conclusion is this, and if you have to show that, right? So correct proof if you have to do, right? For every outcome, please note okay. Then 0 is less than or equal to x sub n of omega, which is less than or equal to x sub n plus 1 of omega. Therefore, the sequence is non-negative and increasing. Also, limit tends tend to infinity xn x omega. So the limit of as n approaches infinity of x sub n of omega equals x of omega. Thus, your zero is less than or equal to x sub n and x sub n increases to x. The monotone convergence theorem now gives you your expected value of x sub n increases to the expected value of x. Why it is correct? Because the sequence that is satisfies exactly the two conditions required for the theorem. Every truncated variable is non-negative, and sequence increases pointwise to your x, right? The conclusion remains valid even when the expectation of x is infinite. Then we have question number 5. Expected stock price in the GBM under geometric non-motion. The equation is given ds sub t equals mu times s sub t dt plus sigma times s sub t dw sub t. The equation asks for the real world expectation, which is your so the expected value under your probability of s t of s sub t, right? We have to find out p of s sub t, right? So assuming constant drift and volatility, we have okay. The expected value under P of S sub t equals S sub 0 multiplied by exponential raised to the power mu t. Under the real world measure, mu is expected continuously compounded growth rate of the stock price. The volatility adjustment appearing inside the lot price. Solution exactly offset. Then the exponential Brownian shock is average. The expected price therefore grows at the real world drift rate. So that is what we have, right? So remember that part. Okay. All right. So these questions are done. Then we have a detailed solution given here. You can see the calculation. The first is again given here. The general expectation formula is given. The the expected value of x equals the integral from minus infinity to positive infinity of x multiplied by f sub x of x dx, which equals the integral from 0 to 1 of x multiplied by 2x dx, right? Which is given. So this is calculated. Then same thing here. We have to take summation, right? We have to take, in other words, we have to take weighted average probability. So for discrete random variable, this is how you do. Question number 3 is very interesting because in question number 3, we are taking the moment generating function m sub x of t equals the expected value of exponential raised to the power tx, and setting the MQF argument close to 1 gives us, the value, this one, right? The expected value of exponential raised to the power x equals m sub x of 1, right? So that is what we have, and that's how we find out this value. Okay. And then we go into here, question number 4. Here, for every scenario, please understand x sub 1 of omega is less than or equal to x sub 2 of omega, which is less than or equal to x3, or so on, x sub n of omega, which is less than or equal to, and so on. As the truncation threshold increases, the truncated value cannot decrease, which is given by your the minimum of x of omega and n converges to x of omega. Therefore, x sub n increases to x. You apply the theorem, which is this. The limit as n approaches infinity of the expected value of x sub n equals the expected value of x, right? Expected value of x sub n increases to the expected value of x. So then we go to last question, which is your problem 5, where we have the solution, right? So this is the equation which is given. S sub t equals S sub 0 multiplied by the exponential of open square bracket mu minus 1/2 sigma square multiplied by t plus sigma w sub t close square bracket. We're taking the expectation under the real world measure, which is giving us this equation basically, and Brownian motion at time t satisfies your w sub t is distributed as a normal random variable with mean 0 and variance t, and using the normal exponential moment formula, we have exponential p okay. Expected value into p of a raise of exponential raised to the power sigma w sub t equals the exponential of 1/2 sigma square t, right? And we solve it, the volatility terms cancel out, right? So minus half sigma square t plus half sigma square t equal to 0. So expected value of p of sub t equals s sub 0 multiplied by exponential raised to power mu t, right? And then we have the risk neutral comparison, right? Okay, and this distinction is very, very fundamental, right? Now, since we have connected this chapter, which was very long, right? So the complete lesson follows one connected chain, basically outcomes and random variables. The random variable converts each possible market scenario into numbers such as return, price, payoff, or loss. Measurability shows that events defined through the random variable have meaningful probabilities. Distribution, your CDF, your PDF, your PMF describe how probabilities allocated across possible values. The correct tool depends on whether the variable is discrete, continuous, or mixed. An expectation converts the full distribution into probability weighted average. Discrete variable use sums, continuous variable use integrals. Probability measures, an expectation is always related to measure the real world. Measure supports forecasting and risk analysis, or the risk neutral measure support no arbitrage pricing. Transformation, function converts one random variable into another. Exponentiating, normal log price produces a positive log normal price. Moments independence, mean, variance, skewness, and control describe continuous or describe distribution space, covariance, and correlation describe how risk factors move together, and drive portfolio diversification. Conditional expectation updates value using currently available information under the risk neutral measure. It becomes the core language of derivative pricing, Martingale and dynamic hedging. GBM connection is Brownian motion or Brownian normal shocks and rate normal log return. Exponential transformation reduces your log normal stock prices. And risk neutral conditional expectation converts the terminal payoff into current derivative values, right? Very long, very tricky chapter, guys. Go back, revise it, understand it. Once you've done it, you'll be totally fine. But at least do it thrice, right? You cannot expect to understand stochastic calculus so easily, right? Stochastic calculus is very difficult. This is a long chapter also, 44 slides, right? So go back, revise it. Once you're done, you will totally fine, right? So we have covered a lot, and revise it twice. I'll see you in the next chapter. Okay, next lesson. Thank you.